So there was this linear-based algorithms, and now we are going to talk about algorithms that are distance-based. So what does it mean when we say distance-based? So this class of algorithm is a class of algorithm that actually tries to calculate the distance between your data point. So earlier what we did was that we actually took one feature, and in my case, I think I took the fair feature, and I took the fair feature and I was trying to predict that if the person is going to survive or not. So let's think of it like this. So for example, if you have X and Y axis like this, and on your X axis, you have fair. So this is a fair of $10. This is $15. Then we have $20 here. And then we have $25. And we go on further higher up. And on the y-axis, we have survived. These people survived. And these people did not survive. So basically, N for no survival and S for survived. Now, if the first data point was that the person paid $10 for their fare and they did not survive, so this is the location of that data point on the map. So it's one data point which had only one feature, which was the fare, and the person actually paid $10 for the fare and did not survive. So that's their data point. The second person was he paid $15 and also did not survive. So this is the data point for the second person. Now the third person paid $20 and he survived. And then there was another guy who paid $25 and survived. And then there could be somebody else who paid maybe $22 and did not survive. So their ranking. So these are our data points. Now I am actually going to change the color of these crosses, and I'm going to make them green, just to kind of highlight the difference. So this green means that people survived, and this black means people did not survive. Now, what this algorithm does is it actually tries to find the distance between. So for example, there is a new person now, and you don't know if that person survived or did not survive. However, they paid $17 for the fare. So if they paid $17 for the fare, they are somewhere, so this is somewhere around $17. So they are somewhere in that line here. Now, did they survive or did they not survive is what we need to figure out. So they are on this on this axis here, and for no survival you would be here, and for survived you would be here. Okay, let's take one step back. Actually, I am going to do one more class here, one more feature here, and I'm going to make that blue. And that, where is the eraser? This is the eraser. No, this is not the eraser, this is the color. Eraser, there you go. Okay, let's do Control Z. Okay, I'm actually going to add one more feature to make it a little bit more easier for everybody to understand. So we're going to add one more feature. And on this y-axis, now the feature is P class. This is the feature now, P class. Now, P class has 3 categories. And P class has 1, 2, and 3 values. And for example, let's add some more people here. So somebody who paid $15, they may also may be traveling in second class, and the black the color black means that they did not survive. And there could be somebody who paid maybe $11 and they were traveling in first class and they survived. And then there was somebody else who paid maybe $25 and they were traveling in third class and they survived also. So they were traveling in third class and they survived. So the green marker for them. So there are some people who survived in third class. There's some people who survived maybe in second class, and there are some people who survived in the third class, in the first class. So people survived. Now there is a new person who's traveling in second class and pays. So he's traveling in second class and pays $22 for the fare. So 22 comes somewhere here. So this is approximately 22. Let's take a different color. So let's take red. So this is 22, and let's make it a little bit thicker so that it makes it easier to view. So this is 22 approximately, and this person is traveling in second class. Because he's traveling in second class, they are going to be here. Now, this new person, we don't know if that person survived or not, so that's why the dot or the cross is in red. What this algorithm, this K-nearest neighbor algorithm, this is one of the most simplest algorithms. What it does is that it actually takes this new person and finds the distance. It finds the distance of this person. How far are you from this? How far are you? So it finds the distance to every data point. It finds the distance to every data point that's there. Sorry, that line should be straight, and they find the distance. And then when it finds the distance to every data point, what it does is that it actually finds the closest point. And in this case, the closest point is right here, which is this green point. So because this is the closest point and this is a green point, and the green point means that the person survived, the algorithm is going to say that this new person who is a red dot is actually going to survive because they are very close to this person who had survived. So they were very close, so they survived. If there was another person who paid the same amount of money, $22, however, was traveling in third class and they came here, now this new person is closer to a person who did not survive. The closest distance is to this person. So this person, the algorithm is going to say they are not going to survive. Now this is called K-nearest neighbors. It is actually finding the distance to the closest point, and when it finds the distance to the closest point, whatever is the closest point, it says you are similar to that point because you are closest to them, and that's how I'm going to decide. What you can also do is you can say that, okay, I am not going to base it on one closest person. I am going to base it on three closest. You don't want to keep it even. You want to keep it odd. Because in odd, you can actually, one is a winner. If there are two people and one of them has survived and one of them has not survived, you have a tie and there is no winner. So that's why you try to keep it odd. So you decide that, okay, I'm not going to base it on one person only, but I'm going to base it on three people. Now let's take this new point and let's see what are the closest people for this new data point. So of course, this black is the closest. Then from this green is the closest. And then this is the second green is the closest. So if we take the three closest people for this new data point, two of them are green, this and this, and one of them is black. So two of them are survived and one of them is not survived. So this new person is going to survive based on three data points. So if you take one data point, it was closest was not survived, so person is not, the prediction is going to be not survived. And if you take three data points, then in that case, there are 2 green points closer to that new data point. So this person, but the algorithm is going to predict that this person is going to survive. So this is a very simple algorithm. All it does is it actually calculates the distance to the closest point. And you can base it on 3 closest point, you can base it on 5 closest point, you can base it on 11 closest point, you can base it on 17 closest points. Depending on how much data you have, you can base it on those. You try not to base it on the closest data point, because one could be very biased. You could be close to a very big cluster of like in this case, you could be closer to this not survived data point, but everybody else close to you is all survived. So generally, you should be in the survived category. We shouldn't be just basing it on one person who's there. So that's why you try not to use just one data point. You try to use multiple data points. So you can use 3, 5, 9, 11, 17, 21, whatever you want to use, depending on how big your data set is. You can decide which is the what should be or the algorithm decides what is the category of prediction for this. So when we use this nearest neighbor algorithm, all it is doing is calculating distance. So one thing that you can see is that if your data set is very large, like it has millions and millions of rows, because it is calculating distance to every data point, and if you use a lot of features, your algorithm will become slow because it has to calculate a lot of distances. So that is why k-nearest neighbors, when the data set becomes larger, becomes slow. And if you start to using a large number of features, then it becomes a little bit slower algorithm. But for normal size data sets, it performs okay in terms of speed. Now, again, this algorithm is already pre-coded in sklearn. So from sklearn.neighbors, we can import k-nearest. So k-neighbors classifier. So we can import k-neighbors classifier. And once we import the k-neighbors classifier, we can use, and because it comes from sklearn, the process of actually using this algorithm and turning that into a model is exactly the same. So you are going to instantiate a class. So we're going to call it knn, and knn is equal to k-nearest neighbor classifier, and this is the instance of our algorithm. So we define the algorithm or instantiate a class of the algorithm. Then we do a training of the algorithm. So we're going to do the fit. And again, as we did earlier, I am going to use X independent features, which in my case was just the fair, and then Y is equal to Y, which in our case was the survived feature. So we can train our algorithm like that, so that the k-nearest neighbor gets trained, and then we can use the k-neighbor to predict. So we can predict again exactly how we did earlier. We can predict on X, and it will give us predictions, and these are the predictions for X. And if you want to save these predictions as k-nearest neighbors predictions, k-nearest knn underscore pred, and then we can look at these predictions just to confirm that they got stored properly. So yeah, so they look good. And very similar to how we did earlier, we can calculate the accuracy score, and we can pass the true values, which is survived, and we can pass the k-nearest neighbors predictions, and we can look at the accuracy in this case. So 74%. So it kind of is performing better against a very basic logistic regression algorithm, because it's just looking at the nearest neighbors. Now, in this algorithm, the K stands for how many neighbors you want to. So if you click here, you can actually pass a parameter K. Is it called K or is it called neighbors? No. All right, let's read the documentation a little bit on this one. So it's n neighbors, and the default is 5. So this decision is based on 5. If I do n neighbors, and if you make the n neighbors as 9, you run this, you train the algorithm and then the model, you can make predictions on that. You make predictions on this model, and now you check the accuracy score, and it's 71%. So by changing the number of K or number of neighbors to base your decision on is basically, again, a feature that you can actually tune to see what kind of accuracy do you get, or where do you get the best accuracy. Maybe you, let's go down a little bit, and instead of going 9, if we go 3, if we base it on 3, what kind of accuracy do we get for that? 75. So it's even 3 is giving you even better than that. So this is how you can actually train your algorithm based on this condition, or based on this parameter that you can actually see that where your algorithm performs better versus not. And again, this algorithm is a very simple algorithm, just calculates the distance between the two data points, and then makes a prediction on that data point, that what could be the possible probability or possible outcome or possible prediction for this new data point. So this, I just made a list of this. These are kind of the steps that you will go through. So you basically import your data, then you do some analysis and visualization of your data, then you clean, so removing and handling null values, outliers, bad data, you take care of those. Then you do some feature engineering, then you can do encoding, transformation, scaling, then you do split, and then you do modeling. Now this split piece you can actually do upfront, up here, right after analysis also. So depending on how you want to handle that is one piece that you can actually do it. This splitting can be done here right after this this analysis and visualization piece. So just keep that in mind, that this splitting piece, this splitting can be done upstream also. This is called upstream. You're doing it way above, or you can do it here, depending on where you want to do it. But this is generally the process that you want to follow when you are doing this, any kind of machine learning algorithm. You import the data, you analyze, you visualize, then you clean, feature engineer, encode, transform, scale, and then you split your training and testing, and then you build modeling on that. You just have to be careful that when you're handling these null values or bad values, you actually do not do you try to avoid data leakage. And data leakage, the concept that we have gone through earlier, is that you try not to influence that result using the test data. So you just want to influence it by using the training data. This splitting can be done upstream also. This is called upstream. You're doing it way above, or you can do it here, depending on where you want to do it. But this is generally the process that you want to follow when you are doing this, any kind of machine learning algorithm. You import the data, you analyze, you visualize, then you clean, feature engineer, encode, transform, scale, and then you split your training and testing, and then you build modeling on that. You just have to be careful that when you're handling these null values or bad values, you actually do not do you try to avoid data leakage. And data leakage, the concept that we have gone through earlier, is that you try not to influence that result using the test data. So you just want to influence it by using the training data.